Hi, my name is Hiro Ono. I am presenting our exciting NIAC Phase 2 concept, the Enceladus Vent Explorer, or EVE. One of the greatest discoveries in planetary science in the 21st century was the geysers of Enceladus, a moon of Saturn, which eject water vapor and other materials into space. These active geysers are considered to be an evidence that this small icy moon has a subsurface ocean, hidden beneath the ice shell that is tens of kilometers thick. Furthermore, the Cassini spacecraft detected molecular hydrogen in the plume, which indicates possible hydrothermal activity in the ocean. Water, energy, and chemicals provided by the rocky core that is likely in contact with the ocean. These are the ingredients for the genesis of life. Does life exist in the ocean of Enceladus? If it does, how does it look like? If it does not, why? The EVE mission would send robots into the geysers to answer these questions. The spacecraft would consist of two types of modules: the surface module, SM, and a descent module, DM. SM is a lander that would land within a few hundred meters from the entrance of an erupting vent. After a landing, it would deploy a single or multiple DMs, which would move to a vent and descend into it. A DM would be a small robot, no more than 10 centimeters in width, that can go through the narrowest part of the vent. There would be little concern in falling because the gravity on Enceladus is 0.01 g. Rather, DMs would have to resist the strong upward jet. In the vent, DMs would perform in-situ investigations using miniaturized instruments such as microscopic imager and a microfluidics chip. Furthermore, it would potentially collect ocean water and ice particles in the vent and deliver them to the instruments on the SM, such as mass spectrometer, for detailed chemical analysis. The goal is to climb down 3 kilometers from the surface, at which the DMs are likely able to sample the ocean water. EVE has a potential to provide the most accessible path to confirm and characterize the extant life in the Enceladus ocean. In our Phase 1 study, we found that the two greatest challenges for EVE are the dynamic pressure due to the upward flow and the potentially very small size of the vent. It turned out that the two parameters depend largely on the eruption scenario. There are two possible eruption scenarios: boiling and cryovolcanic. The boiling scenario is an amicable one for our robot because it would likely offer a greater vent size of about 1 meter or more and a lower worst-case dynamic pressure, which is about 10 to the 4 pascals. On the other hand, the cryovolcanic scenario is a hostile one, where the dynamic pressure, according to our preliminary model in Phase 1, would be anywhere between 10 to the 3 to 10 to the 7 pascal, and the worst-case vent width could be 10 centimeters at the choke point. We cannot resolve these two conflicting eruption scenarios with the Cassini data. In Phase 1, we also performed a trade analysis of mobility mechanisms that can best negotiate such a harsh environment. Considered options included drop sphere, rappelling robot, and climbing robot with various types of end effectors. The analysis concluded that the DM configuration that is most robust to the environmental uncertainty is a climbing robot with an active anchoring mechanism. The study also concluded that the most realistic way to power the DM would be through a tether. We then developed a point design of DM, which might not be the best design, but a reasonable one guided by JPL experts. We evaluated the feasibility of a 3-kilometer descent into the vent using this point design against the 2 eruption scenarios through computational fluid dynamics simulation, finite element analysis, and preliminary experiments in an ice chamber. In conclusion, we found that the EVE mission is likely feasible under the boiling scenario, even under the worst-case condition. On the other hand, the feasibility under the cryovolcanic scenario remained undetermined. The Phase 1 point design can withstand up to 10 to the 5 pascal dynamic pressure, while the possible range in the Phase 1 cryovolcanic model ranges from 10 to the 3 to 10 to the 7 pascals. The newly started Phase 2 study of EVE is designed to address key remaining uncertainties and assumptions. In particular, we will update the feasibility study in 2 aspects. First, we will refine the simple, one-dimensional cryovolcanic model from Phase 1. Further numerical and experimental studies in Phase 2 have a strong potential to result in tighter bounds on key parameters and better characterization of the flow conditions. Second, we revisit the trade on the robotic system of DM. In particular, instead of having a single point design against the 2 very different eruption scenarios, we will develop 2 sets of mechanical and software designs, as well as concepts. This scenario-based trade study approach is justified because a future orbiter mission to Enceladus before EVE should be able to identify which of the 2 scenarios is correct. In doing so, we will build upon the latest developments in planetary robotics at JPL after the conclusion of Phase 1 in 2017. For example, JPL is currently developing a snake-like robot called EELS, led by Ko-Ai Carpenter, which is capable of going through narrow gaps while resisting high dynamic pressure. Ko-Ai Aga is leading Team CoStar, the JPL's entry to the DARPA Subterranean Challenge, or SUBT, in which a group of robots is tasked to explore an unknown subsurface environment fully autonomously. The team won first place in the DARPA competition in 2020. We will also leverage the Moon Diver proposal to the Discovery program, which would send the Axel rover to a vertical hole on the Moon. Ko-Ai's McGarry and Peyton were among the core members of Axel demonstration in the Mojave Desert in 2019. Our Phase 2 trade space includes mechanical aspects such as anchoring mechanism and mobility system, as well as the software aspects such as autonomous perception and planning. After the system trade study, we will create a technology roadmap which will specify the development efforts, expected timeline, and required resources to realize the EVE mission within 30 years. Our aspiration for EVE is rooted in humanity's fundamental desire to end our cosmic solitude. We are still alone. Yet, for the first time in our history, an encounter with alien life is being discussed with scientific plausibility and technical feasibility. EVE is not merely a mission to an Enceladus vent, but to the secret of life.